Okay. All right. Hi, everybody. Welcome to this presentation. Very excited to have Luke Song give a talk on his work. He's finishing up his PhD at Ohio State University, where he's being advised by Yu Su. He's done several internships, and his research is mainly on foundation models and grounding them in reasoning and perception. He's done a lot of work also on kind of more on the vision perception related side of these models with spatial reasoning. I know him from having done an internship at NVIDIA here as well. So very excited to have you, and it's all yours.
Yeah, thanks, Dieter, for introduction. So my name is Chani Song. I also go by Luke for everybody, and I'm excited to give a presentation about my PhD work, grounding foundation models for embodied intelligence. So the foundation models have transformed vision and language understanding, but like real-world agents require more than just perception, and they must plan, act, and adapt. And my research focus on how we can build foundation models to do that. And before moving in, I think I'm really excited to be here specific in AI too, because I think my first journey to this robotics domain was working with AI to source simulator. And actually my first work was using AI to source simulator. And so I'm excited to be here working, giving a talk in AI2, which I had a lot of memories about door simulator when it didn't not work and did work. But it then moved on to some robotics, a lot of robotics experience. This is on the NVIDIA's Redmond office where we worked on some spatial reasoning for robotics. And there I had a lot of fun with other roboticists, like I think the other, Jesse is a postdoc, good friends and other people too. So this was just a quick journey about my experience. So going back to the content, I think we can see we are definitely in the era of foundation models. Like we see GitHub Copilot, we use it a lot. And like ChatGPT, millions and billions of people use it. And this kind of enthusiasm has been transferred to the academic community too, where like around 24 or 25% of papers in Europe last year was on language models. So, and even in CVPR, where you kind of assume it was not really related to language models, like more than 10% of paper was in language models. So this is like a really big interest in academia too, using foundation models, especially large language models, to improve multimodal perception. So what does a robot kind of foundation models for embodied intelligence like require? Like it needs some kind of a generalization across like task and embodiment. It needs to be also a scalable and data efficient. And it also need to have some spatial understanding, like grabbing an object closest to like doing instructions like grabbing the object closest to the robot arm. It needs to have a task level planning capability, like making a sandwich, cleaning up a spill, and so forth. Of course, there are more capabilities that the robot foundation model require, like safety, but I think these are the core aspects that I want to touch on today's talk. So my talk is structured in 3 parts. First, I'll talk about my work on LLM-Planner, using LLMs, seeing if LLMs can serve as a good planner for embodied agents. This deals with scalability and data efficiency because the large language models trained the limited data can plan pretty well in the embodied robotics domain. And also, I want to highlight my work on improving those planning capabilities of large language models with verifiable subgoals. And lastly, I want to go a little bit deeper into foundation models and how we can improve a core capabilities, in this case, spatial understandings for 2D and 3D VLMs for robotics. And of course, there are some other works that I want to briefly mention, like BioClip, which won the best student paper award last year. That works that we presented a vision foundation model for biology. And also another work, Visual Agent Bench, that are featured in the AI Index report this year, and benchmarking foundation models as embodied agents. So, as I described, the core capabilities of robot foundation models are pretty diverse. But where do we actually begin to tackle this problem? One natural point is planning, like translating language goals into actions. This leads us to ask, can the LLM bridge the gap between the language and the actions in the word, actually in the word? So this led to the first work I'm going to share with you today, LLM-Planner, a fuchsia-grounded planning for embodied agents. And this was one of the first works to use large language models as a hierarchical planning for embodied agents. The key idea is very simple. Let the LLMs handle the high-level reasoning and task decomposition, while low-level controllers executed this kind of grounded skills in the environment. This kind of approach allows us to study well how LLMs can generalize across tasking environments when placed in the loop of real robot decision making. And this was very well received by one of the top 5 most cited AI paper on arXiv. So there's a lot of community enthusiasm around this work. In this work, we ask 2 questions. Can an LLM serve as an effective planner for embodied agents? And how can we ground the LLM's plans in the environment? Also, I love to take questions in the middle of the talk. So if you have any questions in the middle, just feel free to just ping me and ask any questions. And so back to the talk. So the first question I want to ask is, can an LLM serve as an effective planners for embodied agents? So in this work, we were one of the first to actually show the LLMs are actually great high-level planners in this embodied task when it's prompt right. So we have given in-context examples of how LLMs, how to complete certain tasks, like in this middle, put a heated egg in the sink, and how the plan works. In this case, a sequence of skills like navigation fridge, open the fridge, picking up the egg, like closing a fridge, and having a test instruction of cooking a potato and put it into recycle bin. And having an object list, also have an object list, which is a visible object list that are retrieved from the environment. And this kind of a prompt structure helps the LLM actually generate plans from the instructions. And this object list grounds the LLM's plans in the environment, so the LLM can make environmental aware planning. So using this kind of prompt format, we found that the LLMs are pretty good at generating a sequence of high-level plans in order to complete a long horizon tasks. And how does this work conceptually? So let's say you're a human asking the modeled robot to cook a potato and put it into recycle bin. And the LLM planner may output some high-level plans like navigation of the potato, picking up the potato, and maybe putting the potato into recycle bin. And the robot goes on to execute these kind of actions, but it sees that it cannot find the potato in the environment, but it's a fridge. So by relaying this information back into LLM planner, we found that the LLMs are pretty good at leveraging its existing word knowledge, so we can modify the plan to be like navigation to a fridge, opening the fridge and picking up the potato. Like it actually tells the robot to actually go to the fridge. That's the most likely place for a potato to be in. So the LLM planner modified the plan accordingly. And lastly, I think another interesting thing we see is that the humans might be using nouns as a recycle bin, but the robot might not understand what the recycle bin means, but it could see something semantically similar, like garbage can. And also relaying this information, we found the LLMs are pretty good at modifying existing plans to think about what's semantically similar, and then actually prompt the robot to go to the update the robot based on what's available in the environment. So you can see the LLM planner, the large language models are pretty versatile in creating a grounded high-level plan in the environment. Next, I want to kind of go a little deeply into how we can actually make the LLMs control robots in the environment. Now, we just talked about how it can output a good high-level plans. So starting with the instructions like make me a coffee, we take any kind of existing LLMs, and we show how we can actually reliably turn into a sequence of high-level plans, like navigation cup, picking up the cup, or like navigation coffee machine. And we can use a low-level controller. In this work, we used a HLSM from VALS, but it can definitely use any kind of a low-level controller, whether it's policy or whether it's another vision language action model that can turn an individual high-level skills into a sequence of low-level plan. So this kind of a hierarchical framing is pretty effective at using large language models connected to a real policy that's operating in the environment. So in this work, we connected to, we evaluated it on the Alfred benchmark from AI2, one of the main benchmark I've been working on for quite a few years. And the example task in Alfred could be like putting a hot potato on the counter to the right of the sink. So in order to do this kind of task, you need to actually locate the potato, like heat it up, and go to the countertop that is actually right of the sink. And we saw that using these LLM planners in the Fuchsia setting, we were able to output all the existing methods at the time, where existing methods could almost score nothing when it's trained on the same set of data. And this kind of hierarchical framing that we have presented in the LLM planner is actually kind of a status quo of what state-of-art vision language action models are doing, like Groot or Hi Robot or even Hamster, where they have a high-level policy like a vision language models or LLMs that can output a high-level skills, or in this case, Hamster, like a 2D pass. And then the low-level policy, whatever it is, can execute that kind of command or that kind of a 2D pass or so forth. So I'm really excited to see this kind of a hierarchical planning capability that was shown in LLM Planner being one of the default way of using this vision language action models or role foundation models in 2025.
Luke, a couple of questions for you. Can I?
Yep.
Okay. So one thing, cool work, but can you mention the differences between, let's say, the LLM planner work that you presented and works like SayCan or SayPlan?
Yeah, so the problem, I think the main core idea, this difference between the SayCan and LLM Planner is that we use, so SayCan is, I think, more of a bottom-up approach, where SayCan, there's a list of skills that is actually combination networkally like generated from the environment, and the LLMs is simply doing a job of discrimination. So if you think about it a little more deeply, that kind of approach actually requires tons of different calls to the LLM, which is, we found it very costly, around cost more than 10 times like LLM cost than in LLM Planner. And also, I think another issue is that in order for the SayCan to work, it needs to have understanding of all the objects or all the action types that are possible in the environment. And I think that can get really big when you deal with more of a complex environment. On other hands, in the LLM Planner, what we try to do is that we actually generate the plans directly from the task instruction. We do not require a separate list of available actions in the environment. So we generate the actions directly from the environment, and also uses also a object list as a grounding for this LLM planner, so it can actually generate a grounded plan. We empirically tested on the Alfred benchmark using also from SayCan and LLM planner. So the LLM planners are much more effective much more cheaper, first of all, and also much more effective at generating high-level plans that are high-level plans, because we found that it doesn't not get confused that much when the environment has a lot of objects or a lot of things to interact with.
A follow-up question, actually, now that you brought that up. So I guess it's somewhat a bit more similar than to the proc prompt style work, right?
Yes.
We also did. But you mentioned that your model doesn't require specification of these actions that the low-level, whatever, execution module can execute or perform. But if you don't require these as input, how do you prevent your model from generating action commands that your robot or your skill just doesn't understand how to do them?
Exactly, same question I had.
Yeah. Just to clarify, when I talk about like, so when I want talk about like the low-level skills that are available in the environment, it's not the skills that the low-level policy can execute, but like I think in the SayCan they require a list of all different action object combination that's possible in the environment.
Oh yeah,
so
that's what I mean.
Yeah. So we don't require that kind of a list of action object pairs in the environment. But we still, in the LLM-Planner, we do require what's possible with a low-level controller. Like if the low-level controller can only do pick and place, we only have those kind of two skills as a part of the prompt for the LLM-Planner.
So it's closer to prop prompt then.
Yeah. Yes. Yeah.
Look, but cannot someone say that the in context examples you have is already representative of all the combinations of action object or skill object things that the robot can do? Because let's say if I have one skill A, how do the LLM know whether that skill A can be applied on object if it's not in the in context example already? And a follow-up question on that as well, that how your tasks were different from your in context examples that you gave. Were there just combination of that, or were there actually where you can ask LLM whether it's doing planning or not? Because again, I don't have issues with you like someone using it this way, but when they say they are doing planning, then okay, yeah.
Yeah. So yeah, I think that's a good question. That's a great question actually. So in the LLM-Planner, we want to fundamentally explore how LLMs can, when just placed into a environment, how we can plan effectively using its word word knowledge. So in context example, is not so. First of all, I think in context example, it's impossible for the in context example to serve as a memory bank for all different kinds of plans, high-level plans as possible in the environment. So I think in context examples here are most used as a kind of a way to ground like the LLMs on how to plan. Actually, I think when we tested it using GPT-3, this was when the ChatGPT first came out. It requires quite a bit of in-context example because it had trouble like formatting stuff. But in the recent LLMs, actually in the GPT-5 or GPT-4, it can actually get out without any in-context examples and do planning directly in the environments. So I think that's so the in-context examples are not actually providing maybe a cheating information about how to complete the task, but more as a way to how to format the prompt, how to maybe execute a skill that is more readable by the low-level controller. Like for example, in the LLM-Planner, the low-level controller requires a sequence of actions like picking up an object, and then after you pick up an object, you have to place an object, and then the in-context example can provide that kind of signal that after you pick up an object, you have to place an object. But if you go a little bit more than that, the long horizon plans, like if you want to cook a hot potato and put it in the countertop, that kind of task is actually uses the LLM's word knowledge more than the in-context what's available in the in-context examples.
Thank you. Right?
Yeah, true.
Yeah, so thanks for all the questions. And so with the LLM-Planner, we learned that the language models can provide a surprisingly a strong high-level plans. But we found that these plans alone aren't enough in long horizon tasks where the agents often drift and lose track of where they are. So this kind of motivated our next work, M-Track, which focused on keeping agents grounded and on track throughout the execution. So given a task like put a hot potato on the shelf, the plan might be first finding a potato in the environment. And then after you go to the fridge and find the potato, you should pick up the potato. But you should not go and straight to put the potato on the shelf because the task requires you to put a hot potato. So you need to kind of cook it and make it hot. So instead of going to the shelf and skipping the step in the middle, you want the model to actually go and heat the potato first. So in this M-Track work, we try to keep the agent focused on this long horizon task and plan a step by step to complete all the subgoals before completing the task as a whole. Yeah, this is a joint work between the Army Research Lab and us, and this called One Step at a Time, Long Horizon Vision and Language Navigation with Milestones. And in this work, we also ask two questions, like how can we explicitly track task progress in long horizon tasks, and how can embodied agents stay on track using explicit subgoal monitoring? So for the first, question, how can we explicitly track task progress? I want to kind of go over the status quo of the long horizon planning that we see, even in nowadays using vision language action models. So you have basically at the time, step 0, you have a scene and language instructions, and the model is going to output some kind of action. And this goes on and on until the model thinks it's done. So in this kind of middle process, you're kind of trusting the agent to fix itself. And if there's error, you hope it is smart enough to actually undo the error. So you see there some vision language action models are actually able to do that, but I think it's still not enough. And oftentimes this kind of error accumulation can cause a catastrophic failure, especially when the actions are causing a irreversible state, like maybe making like you can say slicing a potato, where it's basically irreversible, and so forth. And revisiting the hierarchical planning that we presented in the LLM-Planner, the instruction gets turned into a high-level plan, and the high-level plan is turned into a low-level plan. And we asked, can we use this generated high-level plan as a subgoals and create a way to track each subgoals in this high-level plans is completed before moving on to the next one. So we define a milestone, which is a intermediate subgoals that can guide long horizon success for long horizon tasks. And we define two types of milestone: navigation milestone, which is determining how, if you're at the object, like in this case, navigation chair, is going to be success if the distance to the object is below a threshold. And we define another manipulation milestone, which is in this case, picking up the spray bottle. And this is a counted as success if the object is in gripper or in receptacle. Now we define the milestone. How can the embodied agent stay on track using this explicit subgoal monitoring? And we use high-level plans to control task progress, like given a scene and the goal instructions and some high-level plan generated by an LLM-Planner or something like that. We have an action, and we run the actions through a milestone checker. This is an explicit module that is separate from the model. And if the milestone checker decides the agent has completed the first high-level plan, we feed the agent with the next high-level plan so it can move on to the next action. So if it decides the agent has not completed this milestone yet, we just keep it on the track for the same high-level plan so we can continue doing that until it is determining the current plan is complete. So how does this work in practice? Let's have a plan. Let's have a high-level plan that says turn and go to the sink, and you assume that the agent needs to actually be closer to the sink, and the model will output some kind of actions like move forward, like move forward like 2 meters, like 30 centimeters or something. And we use a name entity recognition model that turns the high-level plans into a sequence of tag and objects, like in this case, navigation to a sink. And we also use a trained mask RCNN that can do a depth prediction to see if we can locate the object, in this case sink, and if we are actually close enough to the sink using the depth information. And using this information from the mask CNN and the milestone we generated from the name and then the recognition system, we run it through a heuristic-based milestone checker, simply in this case, as I described, how close the agent is to the sink. And if the agent has completed the current instruction, the milestone is deemed complete. And we go to the next plan, which is picking up a fork from the sink. And this works with any types of language-guided agents. And we have works with any type of language-guided agent, because this all depends on, we only use the actions that are generated from the agent, and you have an explicit milestone checker.
So Luke, question.
Mm-hmm.
So if I wanted to do the same subgoal multiple times, how would you implement the counting here?
Yes, so Yeah, so that's a good question. I believe that was actually a weakness of this work. So in this current work, we don't have a way. We don't like there's, I think, if the agents get stuck in the one like a subgoal, there's another good way in this work that can like get out of that state. But I think in the if I want to do it again, if I want to have it actually get out of the state, I would actually have it let it explore a bit in the environment and taking random actions. I think that also definitely helps to in this environment getting out of those kind of like a stuck state. But in this work, we don't actually do that, and we just have simply a limit for how many times you can redo the task, and then we just count as an error. Yeah.
Understood. One more question. So current VLAs have, or current VLMs are roughly around 70 to 80% accurate when it comes to detecting failures given a task description. I'm wondering if that's a problem for your module that essentially detects whether the task has been completed.
Yeah, so I think we need a more error detection on different fronts. Like you could do an error detection on an individual skill, like maybe you have failed to grab an object. But also I think you need to have a detection on more of a longer horizon plan, like when you are making a sandwich, you want to have 2 breads and maybe a cheese and maybe a slice of tomato or maybe a ham. So in that kind of more long horizon task, I think this kind of method is still more valuable because we are in this work, we're more focusing on high level plans than on the lower I guess more lower level control of failures. And I think that's a good point because nowadays we have much more stronger like vision language models that can do this kind of error detection on these plans. So if I were to do it again, I would definitely have a much more model-based approach that can check this milestone much more, I think, slightly more effectively. But I think that's a really good point because I think this works were done a few years ago. So I would definitely agree. The method could be using much more advanced modeling based effort that we use now. But I think there's still a value to using heuristic based checker, which is I think still a very effective way when you simply want to do something like if you're close to another object or if you grab some objects and objects in the hand.
Would you expect to give positive examples only or positive and failed examples of a task?
So if I want to train a model to do that, you definitely want to have both positive and failed examples. I think if I actually want to deploy this kind of pipeline so actually trading the data is actually much more simpler because I have this work we propose this working pipeline, and this pipeline can also be turned into something like a data generation for training that kind of foundation models that can do error detection. So I think that's also another way we can use this work and connect it to the more recent research that we do nowadays.
Okay, thank you.
Yeah, so we connected with 2 different state-of-art methods at that time, and we saw that simply adding this kind of milestone-based checking can improve the success rate over by like 50% on in this case LSTM-LL model. So I think this was pretty interesting that we can do this without any training in the model. So M-track shows that we can substantially improve like long horizon planning by keeping agents on track. But like taking a step back, LLM-Planner and M-track both deal with planning, like one at the level of generating plans and others at maintaining them. So this kind of shows what LLMs are capable, but where should we move on from there? How can we build a better foundation model for robotics? So this leads to my work, RoboSpatial, spatial understanding, improving spatial understanding for a 2D and 3D VLMs, oral at CBPR this year. And Robo Foundation models nowadays can be trained on a variety of different environments, from industrial settings to household robots, and can output actions at many different abstractions, like low-level end effector or joint positions, like key points, like from row point, or even like skills from Google SACAN. So while the forms of model or in the environment vary, I think the important question is what kind of capabilities do they all fundamentally rely on? So one answer is a spatial understanding. Regardless of whether a model is trained for house or industrial robots, no matter if it outputs joins, key points, or high-level skills, all of them depend on the ability to reason about where the objects are and how they can relate and how to act meaningfully in the 3D space. So that motivation brought us to this work, RoboSpatial, teaching spatial understanding to 2D and 3D VLMs for robotics, work done in NVIDIA last year in the Stan Birchfield's team. And in this work, we start with the simple visual reasoning, simple manipulation task. Let's say you're a person asking the questions like putting a teddy bear on the bottom of the shelf. And first need to locate the teddy bear. You need to locate the shelf. And you need to then locate the bottom of the shelf because the person asked for the bottom of the shelf. And you have to understand the relative space that's in the bottom of the shelf, how big it is compared to the teddy bear. And after that, you have to determine the fit between the bottom of the shelf and the teddy bear. And after you all did this visual reasoning process as a robot in your head, and then you can do manipulation. So even this kind of a simple manipulation task requires a sequence of visual reasoning process that the robot needs to do using a parameters. So in this work, we try to see if we can capture this kind of visual reasoning process as a data set and train the model to improve this visual reasoning process to do robot manipulation. And of course, there are existing works trying to do this, but they suffer from a smaller scale, and they are simulation-based, like in RoboPoint, and have some sim to real issues, especially because the RoboPoint was trained on not semantically realistic images. And also, the model-based pipeline that we see in spatial VLM has a lot of errors that makes it actually pretty has the model actually learn not a good spatial understanding when we actually train empirically. So in RoboSpatial, we ask 3 questions, actually one more than the other two works. And first, we try to ask what spatial data is needed, how to generate the data at scale, and how does this improve spatial understanding, and how does it work with real-life robots? And first, we try to determine what kind of spatial data is needed, also inspired from the visual reasoning process I described earlier. So in RoboSpatial, we try to keep it more aligned to the robotics domain as possible. And so we have real images from a scan and tabletop datasets. And we also have a diverse reference frames because the spatial relationship really depends on what kind of frames of reference you're referring to. In this case, you can imagine questions like in front of the monitor really will depend on where the monitor is facing. Because if you say in front of the monitor, you probably want to imply whether if you're looking at the monitor or not. In front of the monitor means specific directions in front of the screen. And we also want to make a robot manipulation ready by having questions like point prediction of the empty space and determining kind of object fit if it's manipulation, if we can do some pick and place tasks. And lastly, we form it as a VQA, like can a bin fit from the cabinet, so we can easily fit into the existing learning paradigms for 2D or 3D vision language models. So what kind of spatial relationship did we define in this RoboSpatial work? So we have spatial configuration, which is a 6D relationship between 2 objects. And next is spatial context, which is formulated as a pointing questions of the empty space. And lastly, we have a spatial compatibility, which is asking a object fit between two objects. So going into more detail, spatial configuration is a 6D relationship between 2 objects. Like an example question may be like, is a desk behind the chair? So in this question, the model needs to locate the desk and locate the chair and kind of create a mental 3D map to determine if the desk is actually behind the chair. And next we have a spatial context, which is a 6D relationship between objects in empty space. An example question may be pointing to an empty space behind the chair. So the model has to actually output a 2D coordinate grounded in the image space. And lastly, spatial compatibility is a fit between an object and the empty space. And we ask questions, can the guitar fit in front of the fridge? So the model has to locate the guitar, localize the empty space in front of the fridge, and try to simulate if the guitar will actually fit in front of the fridge. So you can think of this as a one step further than the spatial context question that I've showed you in the previous slide. And all spatial relationships have 3 different reference frames, including egocentric frame, which stays consistent because you're looking at, this is the direction you're looking at right now. An object-centric frame of reference, which stays consistent whichever direction you're looking at, because in front of the guitar stays consistent wherever you're looking at. And lastly, word-centric frame, it stays consistent whichever direction you're looking at. So I think a key point I want to go over, a key caveat I want to go over next, because is that for this reference frame, some relationship may be similar for 2 different reference frames. For example, in the word-centric frame and the egocentric frame, spatial relationship like left to right is basically same. And the difference between the egocentric frame and the word-centric frame is the elevation of the objects elevation of the objects. So now we define what kind of spatial data is needed. How can we generate this data at scale so we can do a learning with the large foundation models? So we create a data generation pipeline that is heuristic based, and that is also freely customizable, and also very scalable, and you can easily generate millions of data points to do this kind of task. How do we do that? We take a 3D bounding boxes from existing dataset like scan or tabletop dataset, and we turn into a top-down map. You can see it's pretty straightforward to turn into a top-down map because you have all the 3D bounding box information available. And using this 3D bounding box information and top-down map, we can annotate 3 different kinds of spatial questions. Spatial configuration, asking is the bin left of the cabinet. Spatial context, pointing to a vacant space in front of the cabinet and output a 2D point. And spatial compatibility, can the bin fit in front of the cabinet? Okay. And all of the questions has 3 different reference frames, like egocentric frame, can the cup fit left of the screwdriver? And the word-centric frame is the soup can below the cup. I think this is an interesting case because in the word-centric frame, the soup can and the cup are on the same elevation. So if you're gonna ask the model in the word-centric frame, the model should answer no. And lastly is the chair in front of the monitor. The model should answer yes, because the chair is actually in front of the monitor, the direction the monitor is facing. And this is all generating using heuristics. And we don't try to bias the model into answering into a specific frame of reference, because we think that aligns more well with how humans understand spatial relationships. And humans often have some ambiguous answers to different spatial relationships depending on what they imply in their reference frames.
Quick question. How do you decide, for example, which of these reference frames is meaningful for which kinds of objects, right? Because for maybe the screwdriver in front of doesn't make quite as much sense, but for the monitor, it's a very clearly specified meaning and stuff like that. How do you make sure it's not mixing and matching them the wrong way?
Oh yeah, that's a good question. Actually, we use a foundation models. In this case, we use GPT-4o to create a list of objects that has a meaningful spatial like relationship, like in this case, in front, or maybe, I guess to be exact, has a face in this case, like a monitor has a face. So we have a compiled list of objects using foundation models, and we actually do a double check, but I think the foundation models are pretty good at capturing that kind of human nuances when annotating which objects has like a face or some special spatial relationships.
Okay, thank you.
So as I said, we take a existing scan data set like ScanNet, Matterport 3D, 3R scan, and even object pose estimation data set like HOPE or GraphSnap. But the method supports kind of any data set that has 3D bounding box annotations. And we actually, after the RoboSpatial was released, we saw it actually being applied to other different domains and improve the spatial understanding for that specific domain. And the RoboSpatial, even though it was released almost a year ago now, we can see that the data size is still compatible with a recent models, recent method that are released recently, like SAT or LLM-Spatial. And we also have, I think we are the only one that I'm aware of, has a publicly released data generation pipeline. So you can modify the data generation pipeline to whatever usage you need. So now we collected, now we define the data and generate the data at scale. How does the data improve spatial understanding? So we created a RoboSpatial home benchmark, which is a test set, and we went to 5 different apartments, and including my apartment, and annotated 350 spatial question answers. So this is like basically out of the domain data set for testing our models. So you can see we trained a bunch of different models. We have more models in the paper, but I share a few of them on RoboSpatial, and we see that improves spatial understanding for all of the models across the board. And we even
yeah, just to I think like SAT also released data generation pipeline.
Oh, really? Okay.
Yeah.
That's
just like
okay.
in case
I'll
future talks, we will
clarify.
talk about it.
Yeah. Thank you. I think that's good to know. Yeah.
And a quick also, somewhat. So how do you think would, let's say, Gemini, which is also doing a lot of pointing and stuff like that, how do you think the most recent Gemini models would do on that benchmark?
Yeah, so we actually have a result from the most recent Gemini benchmark. So currently, I think the state of art using the Gemini, the the robotics foundation models is around, I think 70%, it's like around 70, but less than 80%. So it's definitely improved. I think a lot to go, because I think the human performance when evaluated on this RoboSpatial home benchmark was over 90%, almost over 95%.
Right.
So there's a pretty big gap between what's Gemini even trained with a large data set is possible and the human performance.
Do you think Gemini could improve if you would fine tune it further on your data sets?
I hope so. I'm not sure what exactly data they fine tune, but I believe it will definitely be improved further if we can get some data from my data set. But I'm not sure if they already did it or not, to be honest. So I can't say for sure. Yeah.
Thank you.
Yeah. So we also evaluate other different benchmarks, and we can see improves the numbers a lot across the board. And I think another interesting thing about foundation models is that the Blink Spatial is a benchmark that it has a lot of human or animal images and ask questions about them. But the RoboSpatial data doesn't have any animals or humans. We can see that due to the generalizability of the foundation model, we could improve the benchmark that has humans or animal information. So we actually were able to teach some kind of spatial understanding capabilities in those kind of benchmarks too. And some qualitative examples, like we ask questions like, can the lamp fit in front of an empty space to the left of the bed? And I think in this example, actually, even Gemini, the most recent models, answers no. And with the RoboSpatial training, the model were all able to answer yes. And they kind of do similarly between these questions, like is the remote behind the chair? And we were able to make the model answer yes. And this was, I also want to mention, this is not a grounding issue, object grounding issue, because all the models we have tested were able to output a bounding boxes for the remote chair, which looks kind of small, or this chair, even though it has my cat on top of it. So this is, I think, more on the spatial understanding problem of this kind of foundation models.
It feels like, even to me, a bit ambiguous in this image, right? No? What does behind the chair mean, right? Because there's, first of all, yeah, maybe it's just the reflections. Because behind, I typically mean behind, and here it's more to the side, or is it just me?
Depends on the reference frame.
Exactly.
Yes.
So a person might even say, I don't know for sure. Or a person might ask a clarification question, right? But
yes. Yeah, so I think I think that's a good point. So I think some questions may be a little bit ambiguous if you go a little deeply, because I think some people may say this is not behind, this is maybe on the side, or this is on like, or something like that. But I think in this benchmark we have we try to kind of I think we try to capture I think different kind of cases where this could be right. I think it's hard to capture like really a ground truth answer for all different kind of spatial relationship. But I think that I agree that's definitely some kind of maybe some kind of I guess not a issue, but maybe some kind of some people may have I think issue with it. But I think still this answer, like is the remote behind the chair, could be a valid answer for some of them. But I think it's surprising all models answer as a no. And if you actually check the reasoning traces between these all models, like I don't think it also can't even understand like what why like it sometimes I think that there were some models that actually think the remote was in front of the chair. So I think that's also something the frontier models are still not being able to do. But it may definitely change because a lot of people are working on it nowadays.
Honestly, I would say remote is in front of chair, or from this viewpoint at least.
So, hey, look, I have a question. So I think like, I guess like reasoning trace is something that's more ambiguous, right? So is there like human preference, something that you will look at evaluating? Because I feel that nowadays, a lot of these like spatial intelligent tasks should move towards like human preference. I think we did that for Momo ads. I'm just curious to hear like, is that the next way of evaluating some of these tasks?
Yeah, so I think nowadays, if we want to, I think if I want to do this again, to be honest, I would actually make the answers much more have a distribution. Like in this case, it could be really depending on what you think about what the humans think. They could be like no, or they could be right, depending on what you think is right. So I think it's more important to not have this single binary answer that has yes or no, but more of a distribution. Like it could be no in this kind of cases, it could be yes in this kind of cases. And I think that's the way to go forward in creating much more human aligned models, because eventually we want the humans to use these models and actually understand what the humans are saying. So I think it's necessary for the benchmarks to model this kind of a human alignment, not having some binary answers for all different kind of spatial understanding tasks, but have more of an answer distribution that can match the human's intention of different spatial reasoning tasks.
Also, one more question. With RoboSpatial training here means that you have an existing model and you're fine-tuning it on this data from RoboSpatial?
Yes.
Or you started from scratch with a random model?
No, these are all fine-tuned from existing foundation models.
Okay. Thank you.
Yes. Yeah. Thanks for this great discussion. So, going to me a little further, I tried to wrap it up quickly because I have more things I want to share. So we also do it with RoboPoints, the same thing, and then we were able to see the RoboSpatial training was able to match this to the ground truths, and we connected with a robotic arm, and then we can test it on different spatial propositions like behind, inside, or behind. And we were able to see the model trained on this kind of task were able to do this pretty effectively. And even cases like generalized to a novel verb that was not on our training data set, like picking up the lone objects in here. And RoboSpatial is used by QN and Gemini Robotics. So it has pretty a lot of interest in the community in this kind of tests. And also this is integrated as a pre-training data set for GR00T N1 in from NVIDIA, and then it has around over 2% gain in object detection accuracy for the vision language using as a vision language action model pre-training.
One quick question. So at this point, RoboSpatial is purely a data set, right? Or are there any algorithmic insights that came out of that for you?
So this is a data set. This is a data set only, the work itself. But I think the reason why we want to focus on data set is because data, I think, I have some more work on doing algorithm improvements of improving spatial understanding, but we simply didn't have, when we are doing RoboSpatial, we simply didn't have data to actually do those kind of experiments algorithmically. So That's why we first built a RoboSpatial data large-scale dataset and benchmark that is a good test bed for doing this kind of a spatial testing and training on spatial reasoning. And actually, in the future work session, I have some works that I'm currently working on that can improve this kind of spatial understanding algorithmically. So that's actually currently on ongoing work.
Thank you.
So, so across the community, there's an exciting front on like these kind of different fronts that I described earlier in the tasks. And this kind of highlights where the field is heading. And hence, it's also a challenge that remains. So I think in the future, I'm very interested in these two major axes, like what kind of data is needed and what kind of a reasoning should this model be capable of. Let's start with like the data side. If we want the foundation models to power robots in everyday setting, what kind of data should it be trained on? So look at this. If we take a look at the simple everyday task, clean up the sink, this may look trivial to us, but the robot like facing the scene needs to understand not just what the objects are, or about how to interact with them in the context, like grabbing a sponge, moving the dish, flipping a sponge, and reasoning about like about the sink. So the real question is, what kind of data do we need to provide to enable this kind of understanding? So this kind of sink example needs understanding about spatial understanding how far the sponge is, and physical understanding of how much force should apply to the sponge. And instruction following, like understanding what the task requires, like cleaning up the spill in this case. And like semantic understanding, like understanding what side the sponge is for scrubbing and wiping, because you don't want to grab like a green side to scrub because it's much more less effective than grabbing the yellow side. And lastly, you want the model to understand how to move, how to control the arm in this kind of embodiment to achieve the goal. So of course, you can collect a bunch of different role trajectories to do this, have the model learn, but I think we all know that it's not really a scalable way of do this. And I think my direction is, can we also leverage like large-scale non-robot data set, like spatial reasoning data set, or like from simulation or from generated videos that can provide kind of meaningful supervision? So where do we actually get the data from help? There are like a few main different sources that researchers are exploring today, like in simulation, where it gives us annotated 3D scenes and actions, and internet data, which kind of provides a large-scale visual and spatial information from real homes, like offices, like in RoboSpatial, or like video generators, which can synthesize realistic motion sequences for tasks that we don't have recording of. On the other hand, there are some human-collected sources like glove or human hand or like handle grippers that captures kind of real interaction in physics, but they're also kind of costly and slow to scale because you require a human operator. So the key question kind of becomes, which of the sources can give us data at scale and diversity and controllability that foundation model require? So this leads us to the next direction. Why simulation, internet and video generator are the most practical source of getting a non-real robot trajectories. These sources share three critical components that the physical collections simply can't match. First is, I think, scalability. This grows as compute instead of human effort. You can always have millions of trajectories overnight without a single teleoperator. And second, really diversity is a key. And internet and the synthetic data can capture a far wider range of scenes, objects, and embodiments than any kind of a globe or handheld gripper setup could, and could expose to model to a long tail of the world, which is what we need for generalization. And lastly, we have a controllability. We have, in this case, what it means by we have more fine-grained control over what and how robots learn. And we can precisely vary task difficulty, object placement, lighting, and viewpoints more systematically. And this controllability is, I believe, is essential for curriculum design and studying learning at scales. So together, this axis, scalable, diverse and controllable, makes simulation and internet and video generation, I believe, is a practical path toward getting a non-robot data mix. Of course, these sources give us a powerful but incomplete supervision. So these sources don't feel the world, like they don't capture something like force, contact, or friction. So how can we connect these scalable sources back to real-world physics? So instead of treating So instead of treating real world data as the only training signal, we can think of it as an anchor that grounds the priors learned from the scalable sources. And the idea is to train broadly on simulation, internet, and generative videos to build a strong visual, semantic, and spatial priors, and then fine-tune and align those priors using a much smaller amount of target raw data that can provide real physical feedbacks. In other words, the path forward, I believe, is not to replace raw data, but to amplify effect on learning for foundation models by pre-training on the vast, controllable, and diverse non-robot world, and collecting on robot data when the grounding truly matters, like in physical world, like for contact force or control fidelity, or even visual fidelity. And one of the ongoing work I'm doing is that we are trying to do a spatial pre-training for vision language action models and investigating what kind of spatial reasoning data is actually helpful for building injecting a strong 3D priors to vision language action models. And another direction I'm very interested in is how to reason about how to make the models reason about different aspects, different axes. So in this case, revisiting these images, revisiting the tasks, you also need to reason about spatial, reason about physics, reason about like instruction following and semantic, and also a control. So what I want to really see is that how we can reason using different tools, like even with tools like sensors, like tactile sensors or force torque sensors, or even specialized models like segment anything model or foundation stereo. So you can ground the reasonings into much more richer signal. And I believe this combination can make the reasoning more robust. And actually there's ongoing work that is, I hope is going to be released soon for GDPR. And we try to improve the spatial understanding with multi-turn tool use using specialized models like SAM or depth estimation methods. So to wrap up, my work so far has focused on planning, and task tracking and spatial understanding. But looking forward, I see two key directions for robot foundation models, like figuring out the right mix of robot and non-robot data and inventing reasoning capabilities with the help of tools and specialized models. And I also want to thank my three honorary co-authors, who may have contributed to some typos in this slide, as they love to get on my keyboard. But thanks all for listening to the talk, and I hope it's entertaining and love to get questions from anyone.
All right.
Thank you very much. We have 3 minutes for questions.
I do have one. So would you, how do you view the direction of essentially keeping an explicit 3D map of the environment and having VLAs act on that or do VQA on that?
Yeah, so I think that's a very interesting area that's actually pretty underexplored right now. I think that also ties along with memory capability that is also very underexplored. And in my lab, actually, we work a lot on agentic memory. So whether it's through RAG or whether it's using existing, whether it's RAG or is it simply maybe in context memories. But I think those kind of methods, I think we should definitely, if we want to move on to more generalizable robotics, like we definitely don't want to just simply rely on large foundation models to do everything. Those kind of components are actually, I think, maybe creating an explicit 3D map or maybe had the explicit memory of the environment that you have visited. Those kind of things, I think, only can contribute more to making the foundation models more robust and more generalizable. But I think it's kind of unfortunate that we don't see a lot of work in that area. But I believe those, like even I think including like specialized model like SAM, like those are really good at segmentation, like better than even a lot of foundation models. But like models like even the Robo Foundation model don't use it. Like even depth methods, like they don't use it at all. So I don't think that's the good best way to go. I think we should actively embrace those kind of explicit models or explicit methods, and I think that's the way to go to build a truly generalizable foundation model that can actually operate in the real world.
Thank you.
And on the previous slide, I think you had this where you talked about tools. Can you clarify? So were these, do you mean tools in the robotic sense or tools as computational tools and models that we should leverage?
Oh yeah, sorry, to clarify, this is the tools in specialized models, not the robotics tools like spatialize or something like that. So this is using tools like, is in this case specifically a specialized model.
And for these sensors like tactile, force torque, how are you going to get the training data for those? What are your thoughts on that?
Yeah, so I think that's a very difficult case for this kind of tech. I think that's a very difficult issue collecting data. I think especially for something like a tactile sensor for specific, you can easily, I think, collect a lot of data using not only just robot, but maybe you have a handheld tactile glove. I think there's some works around that. They can collect a lot of different tactile signals. And you can, I think there's also a recent work from Downface group that can learn a joint encoder between a actions and a this kind of a I think it was a video signal, but I think you can actually create a joint encoder between a tactile signal and maybe a visual, maybe a robot pre-perception. And I think we need to have some more work on representation learning for this kind of a tactile sensor or force torque sensor, because there are actually we need to work on more lower data regime than we are dealing with other like data like in the robots. So I think that's actually an issue, and I think there also work in NVIDIA. They use a simulation to have this kind of sensor data, but personally, I haven't actually used those sensors in the simulation, so I'm not sure how much that transfers to actual real life signals in the real world. Yeah.
All right. Thank you so much. It was very interesting work. And we'll stay in touch. Thank you.
Great. Thank you. Thanks for having me. Have a great rest of your week, everybody.
You too.
You too.
Bye.
Thank you, Luke. Have a good day.
Bye.
Bye.